Welcome back. This is an information sheet on standing waves, and we're going to look at standing waves in the lab. A standing wave is anything that's going to generate a pure tone. So if you were to have a guitar string that's vibrating back and forth, and you could actually freeze frame a very, very slow picture and see, say, the vibrations of that string, knowing how far away from middle line it is, and you could see that fundamental. That is what a standing wave is. You're going to see that there's some really cool things that standing waves do. You can have standing waves like this, to where you have some of these raised parts where it's far away from the equilibrium line, and then you're going to have these closed parts where they are touching the equilibrium line, and you can have multiple harmonics, and we'll look at that in just a second. Okay, so remember, a wave is traveling energy through some type of medium. And we look at strings a lot, that you could also do this with air. Air does this. Anything does this. If you were to even hit a railroad track with a hammer, you would get a wave inside the material of the steel as it's going down the railroad track. That's why you can hear sounds through solid objects. Even you're listening to your own voice through your bones. That's why your voice sounds lower than people who can hear you. If you ever heard your voice on a tape recorder and think you sound like a girl, that's the reason, okay? Because you think you're very manly, because you're hearing your voice through your bones. Except you girls, you're never manly, okay? Well, let's look at this. So let's get some vocabulary first. So we're going to start with, this is called an antinode, which is this area that's far away from the equilibrium line. And then a node is where there is no amplitude at all. So you've got to remember, an amplitude goes from this middle line to wherever the height of the crest or the height of the trough. So remember, the crest goes up, whatever up means, and trough down. The node is where there is an appearance of no amplitude at all. And we'll look at this when we study vibrating strings. The wavelength, remember, is two of these antinodes. So a sine wave goes up away from zero line, comes back to zero. Okay, so this would be like 90 degrees, 180 degrees. Then it keeps going to 270 degrees, and then an entire circle is 360 degrees. So you have an up and back and up as a wavelength. The antinode, in the case of a sine wave, is going to be 1/2 of the distance. So the wavelength is going to start with a node where there's no amplitude, end with a node where there's no amplitude, and then halfway in the middle there's also a node where there's no amplitude. If you were to have a vibrating string that has a node and a node, okay, this is called the fundamental of a pitch. It's the lowest possible sound you can make. So if you were to ring a bell, it rings at the fundamental. Okay, if you were to pluck a string, it's going to ring at the fundamental. If you were to blow on a trumpet, the lowest sound you get on that air, in that air tube, is going to be the fundamental. You can get some higher notes. We're going to be able to see by speeding up the air a little bit, you can get different harmonics, and we'll look at that in just a second. But the fundamental is always going to be from a node to a node, and normally it's 1/2 of a wavelength. So a fundamental is 1/2 of the wavelength, because from node to node, a wavelength is then going to be also a second node to node. The wavelength is the entire distance. Okay, so far so good. So looking at harmonics, if you have the first fundamental, which is your lowest pitch if you're looking at music or looking at sound, the lowest pitch is 1/2 of that wavelength, okay, because it's going from node to node. If you were to speed up the frequency to twice that original, you are going to get a frequency of one wavelength. Okay, that's called the second harmonic. The first harmonic is the bottom. The fundamental is the first harmonic. The second harmonic is going to be divided into two, where there's an antinode exactly in the middle. So harmonics are pretty easy in terms of remembering how many antinodes do you have. If you have two, then that's the second harmonic. If you have one, that's the first harmonic, which is the fundamental. And it can keep going. Third, fourth, fifth, etc., 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 and we'll look at this in class. If you see it, examples of fundamental, if you were to have a fundamental of 1 hertz, that's a frequency, and now it goes into exactly 2, then you're going to have 2 hertz. it just multiplies by 2. If you were to have a third harmonic, each one of these antinodes would be vibrating at 3 hertz, and then 4 and 5, etc. Okay, so it's just a multiple of the original fundamental, right? So your frequency, the frequency is going to be the frequency of the harmonic multiplied by the number of the harmonic. So if it's the third harmonic, you're going to take the original frequency of the pitch, whatever hertz that is, multiplied by 3. So pretty easy. Here's an example. Find the frequency of the third harmonic of a 4 hertz fundamental. Well, 4 hertz times the third harmonic, so 4 times 3, you're going to have that as vibrating at 12 hertz. Pretty easy. If the fifth harmonic has a frequency of 55, find the fundamental. Okay. Well, if the fifth one is 5 times the first one, and it's 55, take 55 and divide by 5, and you'll get a fundamental at 11. I hope that makes sense. We're talking about really easy math here. Okay. Non-harmonic waves can be forced into boundaries. We're going to see, like, if you're splashing water in the swimming pool, the water can either go up and down right at the edge of the swimming pool, or the whole water can rise and lower at the edge of a swimming pool. So you can get water to splash up and down here if this is a solid boundary, if it doesn't end at a node. If you can make it end at a node, then you're going to get a hump and a dip that occurs right at the edge of the pool. So I doubt that we're going to be looking very much at that, but waves can also be affected by how they reflect off of surfaces, like walls, if it's sound, or water splashing in the tub or whatever. Okay, I'd like you to try this together with your partners, your lab team or your table partners, whoever, and try to do a good job answering the questions as you go. Please do not just throw something together. Try to answer it well.